Alright, welcome back, MECH1310. Last chapter we're going to go through here is chapter 14, covering transformers. Alright, so basic topics we're going to run through: mutual inductance, basic transformer, what it means if we're stepping up, stepping down in transformers, alright, how we load a secondary, impedance matching, and the different ways we can tap transformers to get different voltages that we need. Okay, so the first concept of what we're going to talk about here is called mutual inductance. Okay, an inductor we didn't cover too much in this course, different chapter in the book. An inductor is really just a coil of wire that holds a magnetic field, kind of like a capacitor stores a charge. All right, an inductor holds a field, so that's why we use capacitors and inductors to filter signals and things like that. Okay, so when we talk about mutual inductance, I want you to think of the word an inductor, which is a coil of wire. Alright, so when we talk about mutual inductance, we put two coils next to each other. They do not physically make a connection. We do not wire them to one another. There is in fact a gap between them. Alright, but what happens is mutual inductance is as we put a voltage through one of the coils, it induces a voltage on the other coil. Just kind of like a Tesla coil. So we have a primary winding and a secondary winding. Alright, so what really happens is that magnetic field, like I just said, the change in flux or the change in the magnetic field in one coil causes it to change or is induced on the second one. Just like we talked about with an induction motor, and we induce the magnetic field, alright, to make the motor turn. So the whole point is I said that they were not wired together. It is mutual inductance. It is the field inducing it to do it. So we call that electrical isolations because the circuits are not connected physically. Now, can you wrap one coil over the other? Yes. However, there's still some sort of rubber coating around the wire that's insulating, or we have air gaps or things like that. So they do not physically make a connection, like a series circuit or parallel circuit or something like that. So we call that electrical isolation in the circuit. Okay, so the mutual inductance, L is the symbol we use for an inductor, kind of like we use C for capacitance. So mutual inductance is going to be L subscript M. So that's the amount of voltage that we have induced on the second coil based on the current in the first coil. So this is really kind of like what it looks like. We have our lines of force, and we talked about that in the magnetic chapter. But what we're really doing is you can see the different flux lines and how they change. The direction of the windings do matter. We're going to get into that in a little bit because they do control the direction of the flow of the flux. Alright, but the first thing we want to be able to calculate is the mutual inductance. So make sure that you got this equation written down. L sub M stands for the mutual inductance. Okay, we have our K, that's our coefficient of coupling. And then we have the square root of L1 times L2. That's the inductance of each coil. And inductance has a unit of henries. Alright, inductance has a unit of henries. So anytime you see an L, I want you to think of an inductor, coil of wire. Okay? And the unit is henries. So there's a few things the coefficient of coupling depends on. The orientation of the coils to each other. Alright, it depends on which direction they're wound and how they are, whether they're perpendicular or parallel, those sort of things. How close they are. Distance matters. So we can space them out or get them tightly close together. And are they common core? Okay, we're going to talk about the different types of cores that we can have in our transformers. So, the coefficient of coupling, okay, it's how well they are linked together. It's a number between 0 and 1. Okay, the closer to 1, okay, the stronger the coupling is. Okay, so we can take a look at this. Coefficient of coupling is phi, this is the Greek letter phi, phi1 minus phi2, okay, or the change in that divided by phi1. And phi represents the flux in Webers, if you guys remember doing that from the magnetic chapter. Alright, so let's talk about this We have two coils, so here's an example wound on a single core, and the coefficient of coupling is 0.3. The inductance of the coil is 10 microhenries. So remember that is 10 times 10 to the minus sixth. Make sure you're doing that with your calculation. And then the inductance of coil 2, okay, or L2, is 15 microhenries. So 15 times 10 to the minus 6. We want to find the mutual inductance. Well, I've given you all the information that you need. You literally just need to plug those into the equation, okay? So when you do that, so substituting in our given values, all right, in for K, for L1 and L2, we end up getting our mutual inductance as 3.67 microhenries. Remember, inductance is in terms of henries, and you're going to get 3.67 times 10 to the minus 6, so we write that as microhenries when we do that. Alright, so let's take a look at example 2 now. We want to determine the coefficient of coupling when the mutual inductance is 2 microhenries. The inductor on coil 1 is 16 microhenries, and the inductance on coil 2 is 14 microhenries. So the first thing we need to do, take the equation that's in yellow and solve for K. So when we do that, we divide both sides by the square root of L1 times L2 because we have to undo the multiplication. So when we do that, this is the coefficient of coupling equation. So Lm divided by the square root of L1 times L2. Now we just simply substitute in all of our given values. Alright, and when we do that, we get 0.25. Make sure that you're putting this in the calculator exactly as you see it here so that your calculator will do the order of operations correctly. So make sure you pause the video and make sure that you're getting both of these answers in your calculator so that you're using your calculator correctly. If you don't get these answers, make sure that you're putting enough parentheses in so that it handles the order of operations correctly. These problems are this easy. It's just a matter of making sure you're making your calculator work through it correctly. Alright, so coefficient of coupling, like I said in this case, 0.25. Alright, so basic transformers for us. What do they consist of? Coils of wire. Alright, in class I'll pass these around so that you can physically see what the transformer looks like. But just lots of windings, very, very many windings, okay? So they're coupled electromagnetically to each other, and we have mutual inductance to transfer power from one coil to another. So remember when we talked about in the magnetic flux chapter, right? When you take a coil of wire, and you put current through it, it produces a magnetic field. Just like when we talk about a solenoid valve, right? We opened and closed the plunger in the lab, right? But we have a coil of wire, we put current through it, produces a magnetic field. Now we put the current through one of the windings here, and it induces that magnetic field onto the other set of windings, allowing current to transfer through mutual inductance. Okay, so three basic types of cores that we're going to look like on a transformer. Okay, so when we draw a transformer, it's two inductors exactly as you see here. So notice that they're still electrically isolated. We're not drawing any wires connected to each other. Alright, but this is the symbol for a transformer. Two inductors sitting next to each other like this. Okay, three basic types of cores that we have. The first one is an air core. So if you've seen the Tesla coil that I brought in potentially, you can see that we have the primary coil, a secondary coil, and nothing's touching between them. It's just air between the two. You'll see a lot of those kind of in your computers as well. Notice on the middle one now, we have dashed lines. Those are ferrite cores. Okay, so when we see two dashed lines, we see ferrite. Okay, that's just the material that we have the windings wrapped around. And then lastly, most common one, iron core. Alright, that's what the windings are around. So two solid lines represent an iron core. So make sure you know those. Those will be on your test. Making sure you know what kind of core that is on the transformer. Okay, so if we look at it schematically, we always read these like a book, left to right. So primary winding will be on the left, secondary winding will be on the right. All right, and we can see the source goes with the primary winding, the load goes with the secondary winding. So when you see these symbols, you know, on a schematic or things like that, know that it's a transformer. Okay, so the primary winding here, so if we have a core, all right, say it's an iron core, we have a certain number of windings, okay, on the primary side, and you can see how there's no electric connection between the two. We just have the flux that transfers through the mutual inductance as the current goes through the wire. That's really all it comes down to. Very, very simple, basic. All right, so different types of cores, not the material inside, but how they're wound. Okay, so if we take a look, this is called a core type. These ones are very, very easy to insulate. So we can see where we have a primary and a secondary winding, and there's lots of wrappings of that wire around. And the number of turns, as you call it, is important. And we're going to get into that. Okay? If we look at this type of winding, okay, this is called a shell type. So the first one's called a core type. The second one's called a shell type. So we can see how those windings go around each other's. Okay, they're around the same leg. All right, that doesn't mean the wire is physically open. Most of the time, this is magnetic copper wire, and with magnetic copper wire, there is a thin insulating material around the outside of it. So don't think that there is metal on metal contact and that we're shorting something. There is not metal on metal contact going on here. The wires are insulated, so there is no short. Okay, so if we have a shell type, we're going to get a higher core flux, all right, which means we're going to get a higher, stronger magnetic field, which means we don't have to make as many turns. So that's really the advantage, I guess, of using a shell type transformer. Okay, you don't have to use as much wire to make it work. All right, but a little harder to insulate since it's wrapped around the middle there. So you can kind of see just a breakdown of what it looks like and how it kind of goes together. I'll try to bring one or two of these in so we can take a look in class. Okay, now the other important part of transformers is phase, right? We've talked about single phase, which is what's in your house. We've talked about three phase. That's what your big motors in industry work on, three-phase power, okay, three-phase electricity. So we can see, all right, what it takes for the windings for the two types of transformers. So the two pictures at the top, those are for core type transformers. Notice the windings are on the outside legs of the core. The bottom type is shell type. Obviously the single phases are on the left, the three phases are on the right. But we can see what the different windings look like and how they're kind of enclosed in the transformer there, and where they notice that three phase, there's a winding for each phase, and so on and so forth. So this is going to be similar to the Tesla coil that I bring in, or I show you in class. As we do this, we have an air core here. So we have loosely coupled windings, all right? That's just a plastic PVC, all right? So we can separate those by the space. All right, so if the bottom one's the primary, the top one would be the secondary, and it would transfer, and notice the only gap there is air. Or we could wind them on top of each other, more like the Tesla coil I do bring in. This one's more similar. We put the primary winding on the outside, the secondary winding on the inside. But remember, the wires are coated, all right, so they are protected, and there's not a short circuit going on. All right, so the way they kind of look unwrapped, okay, upper left-hand corner, three-phase. The kind of foily looking donut, more or less what you're gonna see in like your computer or something like that. It's not really necessarily that size on scale. The bottom right-hand one, all right, you can pull those right out of a microwave. That's what they're gonna look like. I'll bring probably one of those in. And then the nice ones in plastic on the bottom left, okay, those are like for our like DC power sources for our PLCs and controls and that sort of thing. All right. other types of transformers that you see. Most of these, all right, you're going to see inside your computer. You open up your motherboard, or you just look at some basic circuitry that's going on in a cabinet. Not necessarily, inside a PLC or something that small, but basic, a board that you might look at. These are all transformers, okay? Just coils of wire. This is a large transformer, right? So this is like at a substation. So when you're driving by, outside a power station, or when we gotta boost the signal or step things down, right? There's a substation outside of town. Because we transmit at higher voltages. We don't transmit at 480 volts. But this is where it transmits and steps down to 480 volts. And this is where you can transform it down into 220, so on and so forth. So this is a very, very large transformer here. Okay, and notice, why does everything look like a cylinder? I'll reiterate this later on, but alright, so we keep the windings cool. Those sit in a bath of oil. Okay, so every transformer that you see like this, those coils sit in oil so they can dissipate the heat and stay cool. Because remember, electricity causes heat, so we need to be able to keep those cool. Alright, so a couple different types of turns ratios we're going to talk about. We want to talk about ratio of turns in the secondary winding to the number of turns in the primary winding. And when I'm talking about turns, I'm talking about literally wrapping the wire around and how many times it's been wrapped around the core. So that's what we're talking about with number of turns. So there's a turns ratio. This ratio helps us if we're stepping up or stepping down a voltage, how we calculate what that voltage is going to be, or what that current's going to be, or what the power is going to even be. Okay, so the main ratio, okay, is the number of turns of the secondary over primary. So little n is the turns ratio, and then the n subscript secondary is the secondary winding number of turns, and the n subscript primary is the primary number of turns. All right, how many times did you wrap that around the core? It does matter, because we want to be able to step up or step down a transformer to a specified voltage, and that requires a specific ratio. Okay, so when we're going in our house and you have 240 down to 120, you need a specific number of turns to be able to do that, going from the secondary to the primary or primary to secondary. Okay, so most transformers are not usually marked with turns ratios. So that's kind of the hardest part. You can't look at that and be like, oh, that's a 3 to 1 or 2 to 1 or something like that. You're not going to be able to see that. All right, so let's do a calculation here. We have a transformer that has 800 turns on the primary and has a turns ratio of 1/4, or 0.25. How many turns are on the secondary? So in this case, we want to take the ratio, which is 0.25, times 800. I'm just substituting into the equation that's in the yellow box right there. But we're solving for the secondary, so that means I have to multiply both sides by the primary, and it cancels on the right. So I'm going to take the number of turns on the primary times the turns ratio. That will give me the number of turns on the secondary. So you should say 800 times 0.25, all right, or 200 turns are on the secondary. Okay, so the primary has 800 turns. There's a turns ratio of 0.25. The secondary has 200 turns. Okay. Another thing that's always important to pay attention to, the dots on the transformer, those help determine the polarity. Okay, so when we want to do that, we have what we call them phase dots, and you'll see them kind of stamped on the transformer. This is how we can change the polarity. Okay, very important when we're maybe rectifying DC and things like that, when we want to capture only a certain part of the waveform, not the entire part, or when we transform and take the bottom part of the waveform and make it the top part. So when we were doing that rectifier, notice it always came in, AC to DC through a transformer first, so we could grab some things. Moving forward here. So when the dots are aligned on top, we are in phase, and when the dots are at diagonals, okay, we are out of phase. So that's really what it means, and that's how you tell if they're in the same phase or if we're 90 degrees out of phase with one another. Okay, so when we want to talk about a step up or a step down transformer, what does that really mean? Step up means we're stepping up the voltage, Okay? Step down means we're stepping down the voltage. So in your neighborhood, there's probably a 240 volt transformer that steps from 240 down to 120. So that's a step down transformer. Okay, when do we step up? We want to step the voltage up to transmit long distances. All right, over your transmission lines. Okay, so if we take a look at this, how can we calculate the voltage? We can use the turns ratio. So remember, voltage is the same as the normal turns ratio. So it's the voltage of the secondary over the voltage of the primary is equal to the number of turns on the secondary divided by the number of turns on the primary. So just remember, when we're dealing with voltage, it's secondary over primary. Secondary over primary. Okay, and then you got voltage and turns ratio. So very, very important. And then you can solve for the secondary voltage algebraically. You can solve for the primary voltage algebraically, whatever you want to. Okay, but the simplest way, okay, is if we want to find the secondary voltage, we just take the primary voltage times the turns ratio. That's really how easy this is. Okay, so if we have a step-up transformer, the secondary voltage is going to be greater than the primary voltage. Okay, so the number of turns N is greater than 1. So the ratio, okay? In a step-down transformer, the secondary voltage is less than the primary voltage, so the turns ratio is less than 1. Okay? So step-up transformer, the turns ratio is greater than 1, right? Because we're taking the primary and making the secondary bigger. If we're doing a step-down transformer, we're taking the primary and we're making it the secondary smaller, so that's why the ratio has to be less than 1. So making it smaller, the ratio is less than 1. Making it larger, the ratio is greater than 1. Remember, N in this case represents the turns ratio. Okay, so let's take a look at this example here. We have this schematic. We have a primary voltage of 120 volts. We have a 4:1 turns ratio. So be careful on this one. Remember that it is always what? Secondary over primary. Secondary over primary. Okay, so I want you to think about, hey, is this a step up or a step down transformer? Okay, this is a step down transformer. I want you to know that because it is what? Always the ratio of secondary over primary. So what does that mean? You have the secondary voltage, so V secondary divided by V primary is equal to the number of turns secondary, which in this case is 1, divided by number of turns primary, which is 4. Alright, so essentially, when we solve the equation, alright, I'm going to step back a couple of slides here to this one. We're solving the equation that's kind of on the right. It's same as the bottom equation, but the one that's on the right. Number of turns of the secondary over primary, okay? So that's 1 over 4 in our example times 120, which is our primary voltage. So 1/4 of 120. Okay, so when we do that, we get 30. All right, 1/4 of 20 is 30. So this is a step down transformer because the ratio is based on secondary over primary. 1/4 is less than 1, so it's a step down transformer. So make sure that you understand if it's a step up or a step down transformer. Okay, so be careful with this. Understand the turns ratio here is 1:4, not 4:1. So the turns ratio is 0.25. Always secondary over primary when dealing with voltage. When dealing with voltage. Okay? Now, we have a special transformer. Okay, it's called an isolation transformer. So all we're doing is helping boost the signal. Okay? So sometimes you might see these little balls that are on the power lines. Alright, we're just kind of boosting the signal. We're isolating the 120 volts AC. We're cleaning the signal up. Okay, so the turns ratio happens to be 1. So always a test question. You know, what transformer has a turns ratio of 1? It's an isolation transformer. What's an isolation transformer? Because the primary voltage is equal to the secondary voltage, and all we're wanting to do is pass AC from one circuit to another. So we use it as a filter as well. Okay, you're using this as a filter on signals. Okay, the whole point is it breaks the path of DC between the two circuits while maintaining the AC path. So this is how we use it as a filter. Where do we use filters? Well, when you're on your radio and you're turning to a specific radio station, things like that. Anytime you have a signal where you want to filter certain things out, that's what you're going to use. Okay, an isolation transformer. Very, very important. Okay. Here's the biggest reason though at the bottom here, right? How do we block DC? Because the flux does not change with DC. Okay, so we block the DC. Alright, so a special type of ISO transformer. Okay, that's how we pass higher frequency signals from one another. So we want to transmit your satellite signals, your cable signals, your cell phone signals, things like that. Okay, we use an isolation transformer because don't just think of AC as power, think of it more of an analog signal or things like that we want to transmit. Same kind of concept when we break it down there. Okay, very, very important thing to know though, transformers do not increase power. You cannot get more out of something than you put in. Alright, so they don't ever increase power. Okay, just because we're doing a step up, we're stepping up the voltage, means the current might be stepping down. Okay, so you got to think about those sort of things. We're not increasing the power though. The power has to stay the same. Alright, so if the secondary voltage is higher than the primary voltage, the secondary current has to be lower than the primary current. So it's a give and take relationship. Alright, so stepping up the voltage means you're stepping down the current. Stepping down the voltage means you're stepping up the current. That's why a Tesla coil works the way it does. You have one or two primary windings and then you have like 1,000 secondary windings. What are you doing with a Tesla coil? It's a big transformer, but what are you doing? You're ramping up the voltage. So the current's going way, way down. That's why it's safe to touch a Tesla coil for the most part, unless you really have a ginormous one. Alright, but what's happening is you're ramping up the voltage and you're emitting voltage. So that's why you can hold a light bulb in your hand and it turns on. Alright, you're emitting the voltage, so current has to drop because you're really boosting the voltage on this. Okay, and then oppositely, if the secondary voltage is less than the primary voltage, the secondary current has to be higher. We talked about this. Okay, so power is still calculated the same way though. So that's why you cannot increase power. Okay, you cannot ramp it up because you can't get more out than what you possibly put in. So there's a give and take. Okay, very, very important here. Always a good test question. The primary power must always equal the secondary power. Okay, so remember that if you do calculations. So in a real world, we have what we call an ideal transformer. Does it exist? Not really. We want to get close. What's the whole point? We don't want it to dissipate power or lose power. We do a lot of calculations based on the ideal transformer, but nothing is ever 100% efficient. So you do lose, some power on your transformers. But we use what we call an ideal transformer in calculations. Okay, it doesn't dissipate power. That's really what it means. Okay, 100% of the power is transferred on. Alright, so before, remember when we were talking about turns ratios, and I said when we're dealing with voltage, it's always secondary over primary. Because here's the caveat. When we're dealing with current, the turns ratio swaps. It's primary over secondary. So you have to remember this when you're doing the turns ratio. When it's with current, it's primary over secondary, okay, which is the opposite of what it is with voltage. Okay, so you can just kind of take a look at these readings and understand what's going on, right? If voltage is going up, current's got to go down. So we see that in the top diagram. In the bottom diagram, okay, I'm looking at the secondary side, not the primary side. Okay, the primary side's got to stay the same. The turns ratio is either going to up voltage or current for us. So in the bottom scenario, voltage is going down, so current has to go up. Okay, inverse relationship. One goes up, the other one has to go down. Okay, so there is some reflected resistance that goes into it. Okay, when you use a transformer, you can change both the voltage and the current. All right, but the effective load resistance, okay, has to remain the same. Okay, for the most part. Okay, the primary resistance doesn't always equal RL, but we talk about it and we call it, and it's known as the reflected resistance. It's like what it sees. Okay, so the way we calculate that is the primary resistance over the total inductance resistance. Okay, essentially it's 1 over N squared, N being the turns ratio when you do this. Okay, so the primary resistance is 1 over N, or 1 over N squared, times the inductance, or the total resistance of the inductor. Okay, but this is essentially what it's looking like. So that's an I there looking at the transformer. It's total load resistance. Okay, so that's what you're effectively seeing when you do this. If we have a step-up transformer, the primary resistance is less than the load resistance. Okay, if we have a step-down transformer, the primary resistance is greater than the load resistance. Okay, that should make sense, right? Now, impedance. When we talk about impedance matching, very important. We've talked about this in speakers and things like that. Impedance is a fancier word for like resistance in essence, okay? But it has to do with polar coordinates and things like that for us, okay? So impedance, that's the opposition to current flow in AC circuits, okay? And impedance matching, all right? We use impedance for AC, we use resistance for DC, but it's kind of an interchangeable term, okay? We use it to show resistances, okay, and we want to find impedance matching transformers, just like you want to find impedance matching speakers, all right, so that you get maximum power transfer. That's really all we're looking for. Using the load resistance, okay, or the primary resistance here. Okay, so we can use an amplifier because we really want to boost the signal. Okay, but remember, impedance matches is important because of maximum power transfer. We talked about that back in chapter 6 when we had series parallel combinations. And what, this is kind of this full circle, us getting back to this circuit here, and understanding that our load resistance has to equal our primary resistance. Okay? Alright, let's talk about some more impedance matching stuff. Okay, a balun. Okay, that's an unbalanced transformer. Okay, we can use it to intercept signals. Okay, so TV signal or things like that. So a balanced signal, we have two amplitudes that are 180 degrees out of phase. An unbalanced signal, that's one referred to ground. Okay, you might recognize this a little bit. Okay, so on the back of your TV, you used to have a coaxial connection, right? So that's how you connected your antenna, whether you had rabbit ears or a bow tie antenna, or you had one of those array antennas, that had a bunch of those little cylinders, all different lengths. Okay, same kind of concept there. So that's what we really wanted to do, is that coax goes into the balun, okay, and then we can transmit signals and receive signals through that, and then we process it, and watch TV. But it's very important that we have impedance matching. So like a coax line has a 75 ohms resistance or impedance when we do that. And we use that on dipole antennas. So remember, dipole antenna is your old school TV rabbit ears. Not everyone here may even know what that is anymore. You never had to do that or put foil on it or turn it a certain way, or the weather was bad and you didn't get to watch TV or things like that. Okay, so what are we really doing? All right, and what's the point of the balun? It makes the conversion from a balanced line to an unbalanced line when we do this. Okay, what we're doing is we're matching two different impedances. So this is really your old school rabbit ears antenna going into your coax connector into your TV so that you could, receive the signal. So your antenna was 300 ohms, and we had to be able to go to a coax cable that was 75 ohms. So we used a balun, okay, to help do our impedance matching for that. So we has our antenna, okay, which needed 300 ohms to match the 75 ohm coax, so we use the antenna to do that, or the balun to do that, okay? Old school kind of stuff. You can't even do that anymore because everything has to be a high definition signal, which is a little bit more with that. Okay, so here's some different operational losses that can hurt transformers. All right, the windings resistance. Okay, we can have power lose. That's where we're going to lose power in the form of energy. So dissipating power. A magnetic field loss because the magnetic field is being reversed or isn't strong enough. We can have core losses. Okay, usually you have to replace your transformer after that. But eddy currents, things like that we've talked about before. Winding capacitance, flux leakage. Okay, not all the magnetic field's going the way it should. Okay, so you can have flux leakage. So you're not fully inducing on the secondary side, you know, like you should be. Okay, so power handling capability, okay, is dependent upon its ability to dissipate heat. If you safely remove heat, right, the power capacity of the transformer can be increased. And that's why I was telling you earlier, all those transformers sit in a cylinder of oil, all right? That oil helps dissipate the heat away from the windings so that we can have more efficient transformers, okay? Very, very important. Okay, you'll see cooling fins on them as well. Okay, now how do we transmit power on your transmission lines? Okay, we have kVA, MVA, and that sort of thing. Okay, volt amperes is really what we're doing, because power is what? Voltage times current. So we call it, you know, we got a 10 kVA line that we're transmitting. So kVA, kilovolt amperes. Okay, so remember, power is voltage times current, so a volt ampere is just power. Okay, and it's in watts, but we talk about it in kVA when we're talking transmission lines and going large distances with everything. Okay, so you can look on the side of a motor here. All right, so this is a tag on a motor. All right, you can look at this motor, and it says kVA 0.5 kilovolt amperes. Okay, so we have a 50-60 hertz phase. It can operate what? In Europe or in the United States. It's a single phase. Okay, it talks about the two different voltages, 120, 240. All right, and what the low voltages could be, 1632. That's we can still get it operational. Gives you the weight. Okay, so nameplate tag, things like that. But you can see where kVA, kilovolt amperes, still shows up on that. All right, you can even see it on a color handler data sheet that you can pull. So if you got to buy a transformer, okay, you can still see that it's on here. Okay, and we're going to be taking a look here at the different taps. So I just want you to think about all the other good stuff that's on here, how there's a primary and a secondary winding, and what we're going to get into and I want you to look at is on the bottom right hand corner. Notice there's a little triangle. That's a delta. That's the way there's a hertz up. Just above that with the X's, the X1, X0, X2, X3, that's called a Y connection. So this is a delta to Y. And how do I know it's delta to Y and not Y to delta? I'm reading primary to secondary on the screen here. Okay, and we can do different types of taps on the coils to get different voltages. And we're going to get into that, but it's all shown here on the data sheet from Cutler Hammer. Okay, so we always tend to talk about efficiency, right? I've been talking about, you know, the efficiency of a transformer, how much, you know, heat can we dissipate so that it's working more than optimal efficiency. So the way we calculate efficiency, eta, this is the Greek letter eta, don't say n, because n is the turns ratio, so don't get these confused. This is eta. All right, power out over power in. Power out, output over input. That's how we always calculate efficiency. We're just dealing with power here, so it's power out over power in times 100. Efficiency is always going to be in terms of a percentage. Okay, so we want to find what's the efficiency of this transformer here. Okay, on the primary side, what do we have? That's our, okay, our input power, right? And then, so what are we doing? We have our power out and our power in. So we have to find power. Power is what? VI. So you're going to take 120 times 0.020 because it's 20 milliamps. And then we have to use the equation on the right hand side, we have V squared over R. So you got to take 15 squared divided by 100. Okay? So when we do that efficiency, okay, we take our output over our input. Our output is the secondary side. Okay, so that's why it's 15 volts squared divided by 100. That's calculating power on the output divided by power on the input, which is 120 times 20, or 0.020 amps, times 100. Okay, so when we do this calculation, our efficiency is 94%. Alright, so I've given you the kind of the equation, but remember the output's always the secondary side, the input's always the primary side. So you're going to have to calculate on a test the efficiency of a transformer. Okay. So let's say we have a transformer whose primary power is 150 watts. If 10.5 watts are dissipated in the winding resistance, what's the output power to the load? All right. Let's do this quick calculation here. A half watts, you have to do 150 minus 10.5. Okay, so when you do that, 150 minus 10.5 is going to give you 139.5. So that's our output. So we have to take our output over our input. So you're going to take that 139.5 divided by 150. That's going to give you 0.93 times 100. Okay, which is 93%. So it's a 93% efficient transformer. Okay, so first part, right? We had to find out what was the power, the output power if we dissipate 10.5. So it's just 150 minus 10.5. Okay, that's 139.5. So that's the answer to the first part. That's the power, the output power. Okay, and then we had to do output over input multiplied by 100. All right, and get 93%. Alright, I mentioned this a little earlier when we were talking about the Cutler Hammer data sheets. Alright, tapping multiple windings. Okay, we can tap multiple tap the primary or the secondary side to get different voltage. Okay, so iron core transformer here, this is with a center tap. So this is kind of like split phase. So what you might see in your house, alright, on the left hand side we have 240, and then we use a split phase transformer to break that into two 120s. Okay, that's kind of how your dryer works, because two phase doesn't really exist. All right, it's called split phase. So your dryer requires 240 volts, but you're using two 120 legs of AC to create that 240. So it's split phase. It's not two phase with your dryer. Even though some people say your dryer works on two phase doesn't exist. We only have single phase and three phase. Okay, here's where we can do multi-tap on the primary. Remember, the primary is on the left hand side. Alright, so we can be going the other way. Alright, so we can take two 120s to produce 240 to go the other way. So we might need to do that to make a 240 volt outlet for welding or something like that. Okay, alright. So double tap windings, I was talking about this earlier, right? When we wanted to rectify and get a full wave rectifier. So this is where we use the dots and we use polarity, because remember, when we want to rectify, we want to eliminate the negative portion of that AC signal. And remember, we had the half wave rectifier that either wiped out the negative version, or we had the full wave rectifier, which took that the negative part of the waveform and made it positive to get the full waveform. Okay, and then remember, we talked about this when we were doing like capacitors and things like that, how capacitors leveled that out and made DC. Okay, alright, so this is the most common one. You know, outside the classroom here at Oakland, we have this literally right outside. We'd walk out and take a look at it so that you could kind of see. You know, most people have this, you know, in a neighborhood outside your house. Sorry, I can't speak today. You know, but you have your pole that goes up, your power line that goes up. You have your big cylindrical transformer that's sitting there. All that's sitting in oil. And we pull different taps off of it. So you might have 7.2 kVA of power coming across here. All right. and we're going to do different taps to pull off all the different 120s, and then you service that into your building, and then you can use your transformer to take those two 120s and tap it up to 240, okay, or use your split phase. Notice that every pole there's that wire going down. It's earth ground. You got about a 6-foot rod sticking into ground there for protection and grounding. But this is really what's inside those big cylinders that you see when you're driving down. It's just a big transformer, all right, and we have different taps that we can use to get different voltages, okay? Just an example here of what different taps look like, all right? We have two primary taps on the secondary on the first one here, and then same, we can have them in parallel or in series. So just, it kind of just depends on what we're looking for when we want to get these multi-tap windings out. So three-phase power, right? That's how we transmit all the power, through your power lines and things like that. So how do we get this? Three-phase transformer, okay? It just depends on your hookups, all right? And usually when you get a transformer, it's going to show you how to wire everything up, okay? And we're going to go through how those happen. So remember on that Cutler hammer data sheet that I was talking about earlier, when we had the delta to Y, Y to delta, okay? So this is important. We did some of these calculations in our circuit analysis class when we did a series parallel combination. All right, it kind of just depend on the different legs we were looking at. But those were all of our deltas or Y's or how we calculated those. Okay, so in this scenario, we have our Y on the left-hand side, that's our primary, and then we have our delta on our secondary side. Okay, and it's how we get these windings, okay, to do step up, step down, how we want to tap it, and do those sort of things, okay? So we can go delta to Y, delta to delta, Y to delta, and Y to Y. So there's different kinds of transformer combinations. It's just kind of what we want to get out of it, okay? So if we want to go delta to Y transformer, we designate, okay, A, B, and C primary, and A, B, and C secondary. So if you notice on here, each one of these, there's A, B, C. On the left-hand side of A is primary. On the right-hand side of A is secondary. Same with B. The left-hand side is primary. The second-hand side, or second half side there, is secondary. Same with C, okay? Lefts are primary, rights are secondary. Okay, so it's very important. Everything is numbered, okay? There are specific wires coming up when you do this. So a way that you want to go, we're going to go delta to Y. So in order to do this wiring up, you're going to connect Y, the primary on A, 1 to 10 on C, right? 6 and 9, okay, 5 and 2, and then what? So those are the main legs of the Y. And then where that center tap goes in, the 4, the 8, and the 12 are all the same connection, okay? Same with the 3, the 11, okay, and the 7. Those all make the same connections right there. Okay, so this is what it looks like down here. This is the schematic piece. So you can see on the delta where the 2 and the 5 connect. You can see where 6 and 9 connect, and you can see where 1 and 10 connect. And then we can look at the Y. Okay, notice the 4, the 8, and the 12 are all common. They're the middle node there on the Y, and the 3, 7, and 11 are all the legs of the Y. Okay, so there's how you relate the schematic to how it's wired up. Okay, those of you, in class sitting at Oakland, we have, I'll have this upstairs. Those of you, Motlow, if I remember to bring it, I'll bring it in so I can show you guys. Got one of these transformers that's a delta to Y, so you can kind of see what it looks like when you wire it up. Okay, so why do we do this? Okay, this is a Y to delta. So notice your power lines. Think about what they look like. Up there you have those strands of power lines. So this is your three-phase utility power coming in on a Y. And then when we want to distribute that, to your house, we want to put that on a delta with a center tap. Okay? Notice, why do we do this? Because on the Y, each one of those is a separate phase. Phase A, phase B, phase C. On the delta, we can take phase A and split it, right? Phase A is 240, but we can split that into two 120s on the center tab. We could do the same thing on the left side with B and the same thing on the bottom with C. So there's why we do a Y to delta, okay? Main utility voltage coming in as a Y, delta is at your residence, so that we can center tap that and get the voltages we need. Okay, so key terms for you guys, make sure that you know all these. They will be on the test, all right? They are at the end of the chapter in your book, but I'll just go through them here so that you have them and can pause the video and write them down. We've done in here, okay? And this is the last chapter. All right, so after this, all this stuff will be on your final, so I expect you to know that. But once again, email me with questions or ask me questions in class. Else, guys, have a great day, and I will see you guys in class.